Welcome to lesson number 1 of the NumPy crash course. Let us first discuss why we should use NumPy arrays. Why not use Python lists? At first glance, arrays appear to be very similar to Python lists, although they are more convenient when dealing with numeric operations. A one-dimensional or multi-dimensional array generally consists of a homogeneous grid of values that are all of the same type, whereas lists would be the Python equivalent of an array, but are heterogeneous in the sense that they generally contain elements of different types. This is the most obvious difference. A more subtle difference lies in their functionality. NumPy arrays allow vectorized operation, such as element-wise addition and multiplication, which is a lot more concise than how it would be done with Python lists. Its concision ensures clean code when dealing with numerical operations. Let's have a look in Jupyter Notebooks, where we compare vector addition with plain Python code versus vector addition with NumPy. We'll create two lists with the range function. Make a variable, list2 is equal to a list that ranges from range 1 to a stop integer of 4. Recall that the stop integer is exclusive, stopping at the integer previous to it. And set another variable, list3, equal to a list that equals the same thing, range from 1 to 4. We'll set one more variable, listsum, equal to an empty list for now. There is a reason why I named one list2 and the other list3. The goal is to raise every element in the first list to the power of 2, yielding 1, 4, and 9. And every element in the second list to the power of 3, yielding 1, 8, and 27. Then we want to add these two lists, resulting in the list sum of 2, 12, and 36. We'll first try this with Python lists, and then we'll do it with NumPy arrays. With our list, what we'll do is we'll declare a for loop. For index in range 3. The number 3 corresponding to the length of both lists. We made 3 our stop integer, that way the indices that we'll iterate through will be 0, 1, and 2. If you're not familiar with what we're doing at the moment, make sure to look back at the Python crash course where we discussed for loops. I can then access and modify each element on both lists with the index that's being iterated through. We'll start with list2 index. So every element on list 2, according to the index that's being iterated through, we're going to set it equal to itself. List 2 index, but we're going to set it equal to itself raised to the power of 2. We'll also do list 3 at index. We'll set that element equal to itself raised to the power of 3. Giving us the required values. Inside the for loop, for each element that we're modifying in list 2 and list 3, we'll add them up and append it into our list sum. That is, listsum.append will add both elements that are currently being iterated through and modified. List 2 at index plus list 3 at index. And now, outside of the for loop, if you print the sum, print list sum, we get 2, 12, and 36. Now that was a lot of work. There is a reason why NumPy is known to be a lot more convenient in numerical operations. Because with NumPy arrays, all of this could have been done with 3 lines of code. No looping necessary. We'll give it a try. To begin using NumPy, we'll have to import it. Import NumPy as an alias np. This imports all the submodules and functions from NumPy, which can be accessed from the alias np. We'll first make use of the NumPy arrange function. We'll set array2 is equal to NumPy np.arrange 1 to 4. Arrange is very similar to the range function that we saw in the Python crash course and are currently seeing right now. They are similar in the sense that they both have a start, a stop, and a step, even though so far in this lesson we've only made use of the start and stop integers. The stop integer works the same way as it would for range. It stops at the integer previous to it. So we're going to have a sequence of integers 1, 2, and 3. The main distinction between the two is that range would create a list from 1, 2, and 3, but arrange creates an array from 1 to 3. We can print this for clarity. Print array2, and indeed that is what we get. It's very important to recognize this as an array, not a list. Notice an array doesn't have any commas. The array is a specialized data structure intended for numerical data. We'll discuss it in more depth in the next lesson. For now, this is an array, and to raise every element of this array to the power of 2, all I have to do is just raise it to the power of 2. Run the cell, and this works out perfectly. It raises every element in the array to the power of 2. If you try doing this with a list, we'll comment this out for now and raise one of the lists to some power, and Python yells at us we're not allowed to do that. That's one advantage of working with arrays. We will do the same thing for the second array. Array3 is equal to, copy and paste the following, and we'll change this to a 3. We're setting all elements of this array to the power of 3. And if we print this, print array3, accordingly it outputs an array with each element raised to that power. Finally, we just need to add the elements of these two arrays. We'll delete these print statements for now. And we're just going to print array2 plus array3. Run the code and it outputs the expected result, all within 3 lines of code. If you tried to add 2 lists, as we saw in the Python crash course, it would simply concatenate them. Whereas with arrays, it took the summation of each homologous element. Before we end this discussion, we talked about element-wise addition and exponents. But some other operations that we can take advantage of are subtraction, multiplication, and division. However, aside from basic mathematical operations, NumPy also offers us a wealth of universal mathematic functions that we can use to operate on our array. All of these universal functions performing element-by-element operation over our array or a set of arrays. We'll go over that later on. For now, we'll go over some common mathematical functions accessible to us through NumPy. The first one being NumPy, or np.power. What this does is it will raise all the elements of our array by a corresponding power. np.power, the first argument is the array itself. We're not going to use the arrange function this time to make our array. We'll try another method. On the basis that, in general, numerical data arranged in an array-like structure in Python, such as a list or tuple, those can be converted to arrays through the use of the array function. Array, taking in a list or a tuple, whichever one you want, a list of 1, 2, and 3. This will convert our list to an array. Now that we have our array, the second argument will be the corresponding power. It will be to the power of 4. If we run this, array is not defined. I forgot to add the np alias, which gives us access to all the submodules and functions from NumPy, so don't forget to add your alias, np. If we run this again, notice our list enclosed by the array function. Indeed, this is an array because if we print it, outputs the array itself. Now, alternatively, we could have just written np.array and raised it to the power of 3, as we did previously. This would have worked as well. But it's good to be mindful of universal functions. We'll revert this back. Another commonly used function is numpy.negative. The first argument being our array itself. We'll just copy the array that we have over here. This function speaks for itself as it simply returns an array with negative values. Forgot a parentheses, and there you go. Let's also print this. And now, notably, we have access to the exponential function, np.exp. And we'll take the exponential of every element in our array. And you know what? Instead of copying and pasting this over and over, what we'll do is we'll create a new cell with Alt-Enter and set a variable sample array is equal to np.array 1, 2, and 3 and replace it at every instance. And now we'll take the exponential of every element in the array. And indeed it does take the exponential. We can also use the log function, np.log, which takes the natural logarithm of each element in the array. We can output this and it takes the natural log. We can also make use of trigonometric functions. All trigonometric functions use radians when an angle is called for. Recall that the ratio of degrees to radians is 180 over pi. We can take the sine of all elements in the array, np.sine, sample array, and it takes the sine of every single element. This was a very simple example of why NumPy is more convenient than normal Python code when it comes to numerical operations. We first demonstrated that vector addition is clearly a lot easier with NumPy, such that we're also given a wealth of universal functions that we can use to operate on these arrays, element by element, all of which can be accessed in documentation. With NumPy, indeed, there are many mathematical functions that will make our lives easier. A lot of vector and matrix operations are available to us. However, it also goes beyond convenience, as NumPy arrays also have smaller memory consumption and high performance relative to their Python list counterpart, ideal when reading or writing from several large terabyte files. Now that we know why we need NumPy, in the next lesson, we'll discuss the multi-dimensional NumPy array object.